over here stands for tropicalized ion battery, batteries which can work resiliently in the conditions that we have and can be built with materials that are available within the country. And with this, we have chosen to progress technology advancement in LFP as well as LTO cell chemistries. And with what happens with LTO is that you get a chemistry or a solution which is long life and rapid charging. At the same time, when you progress LFP technology, you get the solution for cost efficiency as well as long range. So the combination of these two chemistries, we can solve for all the requirements that we have, that we can possibly imagine about in the country, whether it is electric mobility, whether it is energy storage, or whether it is any other battery application, even including space research and space exploration. So Hemant, can you tell everybody about that? Why are the right combinations of anodes and cathodes important for these resilience and long life and reliability from the cells?
So when you're designing a cell, the safety issue comes in how you choose your anode and cathode, because it's a cascading reaction that happens, and that builds up the energy and leads to explosion, which you saw in case of NMC. So when you have high voltage cathode and high voltage anode stuck together in one cell, when the thermal runaway starts, the anode degradation starts, and then it has an impact on the cathode. And what ends up happening is too much energy accumulated in a defined volume, and it leads to the fire explosions. Now, long-range strategy is that you use the low voltage anode, low voltage cathode. That would be the ideal state. Because it comes with less energy density, with high price, so we cannot do that. The right way, the best way to do it is you use high voltage anode combined it with low voltage cathode. You use low voltage anode and combine it with high voltage cathode. That's what we are trying to do with our LFP and LTO chemistries over here.
Absolutely. So while you can always choose to combine the high voltage cathode with high voltage anode and have the highest of energy density, but at what cost? At the cost of reliability, at the cost of safety, and at the cost of life that you can drive out of these chemistries. That's why it is best to combine low with high and get LFP and LTO chemistries. Now let's talk about what these chemistries offer. For example, if we look at LTO, it is very good, and as you have seen, safety, reliability is out of question altogether. Even in life, it has the longest life in cell chemistries. It has the highest power density, hence the rapid charging. But yes, it does have limitations on the cost side as well as on the energy density side. But even on the cost side, if you look at it, the cost is also a relatable factor. Whether you're talking only about the upfront cost or you are talking about lifetime amortized cost. With higher upfront cost but a 5 times, 10 times longer life, the running cost or the total cost of ownership that we talk about in the industry is far lower. Now coming to LFP on this side, it is a common man's chemistry. It has a mix of almost everything, a slight bit of shortfall on the power density side, and we can always like to have more energy density packed into LFP as well. So as we go forward, we would like to talk about how these technology advancements are coming about at Log9, what are the various partners that we are working with to make it happen, and what are the interventions that we are doing. Let's talk about the chemistry interventions to start with. Here, the target is that we improve the energy density of the LTO technology by 76%. And that would make it worthwhile for any kind of intra-city mobility application and all sorts of stationary energy storage applications. Hemant, can you tell everybody how we are going to do it?
So what chemistry interventions that we are doing is to first shift to a low cobalt cathode. LTO, as I mentioned, it has a low voltage anode. We want to combine it with high voltage cathode. Generally, that's cobalt rich. That's the state of the art. But what we want to do is to move beyond that. because there are huge supply chain issues on the cobalt-based materials. So there we are expecting that by doing so, we can increase the capacity of the material and increase the energy density by 8%, followed up by removing the cobalt, through and through. We'll have 0% cobalt in our cathodes, and we'll shift to the manganese-rich chemistries, which will boost up our voltage a bit and increase the energy density by about 10%. And the third intervention that we are doing is to shift to zero strain, high capacity anode, which is XNO anode, and overcome the limitations of the LTO side. And that way we can increase the energy density by about 48%. So all in all, we can increase the energy density by almost 76%, which will be a huge boost to this technology.
And with energy density improvement, we get two things free of cost. One, we always like freebies, right? We get cost benefit and we get self-reliance at the same time. So as we move to this kind of energy density improvement, we are looking at a 7% reduction in price, dollar per kilowatt hour, from our intervention on low cobalt rich cathodes, then further 32% with manganese rich cathodes coming in, and another 15% coming in from the intervention on the anode side. So all put together, we will have more than 40% of reduction in the cost of LTO technology upfront itself.
I think when you talk about LTO, the elephant in the room is the cost. Everybody comes up and say, how would you make it cheaper? And I think this is the way, this is the roadmap of Log9 to make it cheaper and make it economically viable.
Now let's talk about LFP. How can we really advance this technology as well? And the way we are looking at it is to kind of switch from smaller format LFP cells to larger format, which improves the energy density by 5% automatically because you have less dead weight in the system. Then we improve the cathode by doping it with suitable elements so that you can further improve the energy capacity of the cathode, leading to a 15% benefit on energy density side. And then finally incorporating silicon-rich anodes to further improve the energy density of the entire cell chemistry. So overall, looking at a benefit of around 27% increase on the energy density side. But this is not where we are stopping. It is not only about advancing the chemical formulations. It's also about looking at the right choice of cell design, the cell format, and at the same time, the processing techniques. So let's talk about cell formats. So we typically have three types of cell formats: cylindrical, pouch, and then prismatic. When we talk about the benefits of the cylindrical format, there are many. Hemant, can you help us with that?
So if you look at the cylindrical form factor, and the reason we want to particularly focus on that first is cylindrical form factor has been, available throughout our life. We have seen the Duracell cells which have been available in cylindrical form factor. Now, what happens is over the years, because of the improvement in the technology, because of the more automation that comes on the cylindrical form factor, you have lesser wastage of material, almost by 50%, when you're fabricating a cell. The other thing is the cylindrical form factor is very, very, intrinsically it is suitable to withstand the pressure, right? Just imagine pressure cooker in your kitchen. Now, in Indian environment where temperature is higher, when the undesired parasitic reactions are, more prone, there's more gases that come out, cylindrical form factor will give you a resiliency to withhold that structure, withhold that shape, as compared to pouch cell or prismatic cells. We have seen in the market, the prismatic cells, because of the long-term storage in the even in the inventory or the vehicles put on the road, the cells deform, which is something that won't happen in the cylindrical form factor. There's high throughput. It comes back to the technology that has been developed, the automation that has been done on the equipment side. And because there is a high throughput, there is a 6% lower cost when it comes to a bigger scale production.
So, Hemant, given that cylindrical had so much benefits, right? Why did people look at prismatic formats, for example, when they wanted to have larger capacity cells?
So prismatic cells are good because a lot of energy can be stored in those cells. And the reason for that is the casing itself are bigger, and you can use thicker electrodes to hold that capacity in. Now, even though that there is a prismatic form, what happens is the cell to pack. When you take the cell and you make the pack, there's more efficiency and there's more energy density that can be available on the pack side. But there is a big but over here. With India's first tabless technology.
So basically, those are the challenges. But with introducing India's first tabless technology, and which will enable us to create high capacity cells with all the benefits of the cylindrical format. And this will lead to better power, better energy, and still provide resilience and high throughput on production side. What we are talking about here is 20 times more energy packed into one single cell as compared to smaller format LFP cells. And at the same time, 24 times more power packed into the same cell. So that's the reason Log9 has chosen to progress the cylindrical format for our cell chemistries. And we already have them here. So this is the kind of cell, what you plugged in was smaller, 20 of those cells can fit into this one single cell. And when you have that, you have lesser number of cells going into a battery pack that reduces cell-to-cell variability at the pack level, ensuring more reliable, longer life packs to happen, at the same time ensuring that your manufacturing becomes simpler and more cost-effective.
Actually, I want to add one more thing here, that because of the tablet structure, the cooling system that you place, because there is a asymmetric dissipation of the heat, it's much easier to remove the heat when you connect those cooling connectors on the tab of the cell. So making those cooling systems even get easier for any manufacturer who is making the battery packs.
And then comes the process. With process innovations, you can further drive down cost, improve sustainability of manufacturing, and lead to better cells coming out of your assembly line. Hemant, would you like to step us through it?
So I think one thing is everybody is focusing on lithium-ion batteries should not be a greenwash to the environment. We want it to be impactful. We don't want to create so much emissions while building the lithium-ion batteries and then end up creating those emissions altogether when we are manufacturing them. So what we have been working on is aqueous-based slurry preparation, where we are not using any organic solvents, where it's easier to remove those solvents when the slurry is coated on the electrodes. And what it does is two things. First is that it reduces your dependency on the organic solvent, which are not good for the environment. Second, because it's easier to dry these aqueous-based electrodes, the amount of energy, heat energy that you're required to dry the electrodes is much less. And when you take both in consideration, you have 20% lower CO2 emissions, which aligns with our goal of creating a greener future with lithium-ion batteries. Because you don't need controlled environment, controlled humidity environment, you have 3% reduction in the capex of setting up the infrastructure, and less operational expense means that you have 7% reduction in the cost per kilowatt hour.
And that drives down cost further and improves efficiency. So the constant effort is to progress technology, advanced technologies towards sustainability and cost efficiency. And the last part is about once the cells are made, how can you improve efficiency over there?
So I think most of the people who know about lithium-ion batteries know one thing for sure, that the formation process takes a long time, and the formation process is very expensive and takes the maximum footprint in the factory. So what we are working on is to develop fast formation process, which will reduce the process time by 40%. And those who are a bit non-technical and cannot understand that, I cannot emphasize on this 40% number, because it makes a huge difference when it comes to the throughput of the factory and further reduction of the cost. We will be reducing the equipment footprint by 35%, and in this process, because there's less equipment required, there's less capex required, we can reduce the price by 6% dollar per kilowatt hour.
Want the metastable slide.
And in total, if we take everything in consideration, Log9 intends to decrease the price of lithium-ion cell on the LTO side by almost 60%. And with LFP, we intend to decrease the cost by almost 35%.
So, one question which got left behind was what do we do about the lithium requirement? How do we solve for lithium availability in this country? Don't worry, we have thought about it. There is a startup which we are supporting